Hello folks, this is Mike coming back at you with another video on precalculus. In the previous video, we looked at the graphs of our 6 trig functions and we talked about amplitude, period, and phase shift. In this video, we are going to talk about inverse trig functions. Now the fun begins. If it wasn't fun already for you, now we're really getting into the good stuff. So, as the title suggests, we are going to talk about the inverse of some of our 6 trig functions, specifically sine, cosine, and tangent. Well, if you think back to our chapter on exponential and logarithmic functions, we said that a function has to be one-to-one in order to have an inverse. Just as a quick recap of the definition of one-to-one, distinct inputs yield distinct outputs. That is to say, if x1 is not equal to x2, then f of x1 is not equal to f of x2. But if we look back at the graphs of the sine and the cosine and the tangent functions, that is not the case. We have, for each of these functions, we have infinitely many inputs that when you plug them in, you get the same value out. For example, if I take minus pi and pi, and I plug them both into the sine function, I'm going to get 0. So that thing's not one-to-one there. The cosine function, I can take 0 and 2 pi and plug them into the cosine function, and they're both going to give me 1 out. And there's infinitely many other x values we could choose for infinitely many y values. So on their entire domain, these things are not one-to-one. So how are we talking about the inverse function when the function is not one-to-one? And that's what we need in order to have the inverse. Well, what we're going to do is a little trick. It is completely valid. We actually do this for a more basic kind of function, but we just don't really clearly state it ever. We're going to pull the trick of restricting the domain of our function. If I take a look at the graph of sine x here, if I only look at x values between and or equal to minus pi over 2 and positive pi over 2, what I have in between my fingers there, the function is one-to-one on that particular interval of x values. As a quick recap, one-to-one functions pass the horizontal line test, which means if you draw a horizontal line anywhere on the graph, if your function is one-to-one, then each horizontal line will intersect the graph in at most 1 point. So you can do that with this interval of x values here, and you will get a function that's one-to-one. So for sine, if we restrict it to inputs being between and equal to minus pi over 2 and positive pi over 2, we get a function that's one-to-one. For the cosine function, if I restrict my domain to be x's between 0 and pi, then that's one-to-one, and we have the inverse there. And then for tangent, if we restrict the domain to be anything between, strictly between minus pi over 2 and positive pi over 2, then we get something that is one-to-one. So when we pull these little tricks, we have our inverse function. So that's what I have right there. For these 3 trig functions, over those particular intervals, the function is one-to-one, and then we have the inverse function. The inverse functions are written as such. The inverse sine is sine and then seemingly exponent of -1 and then x, also written as arc sine x. that takes in x values between or equal to -1 and +1. And it's always going to spit out something between or equal to -π/2 and +π/2. The inverse cosine function, cosine and then -1 exponent and then x, or arc cosine x, has the same domain, takes in things between or equal to -1 and +1, but now what you get out of it is something between or equal to 0 and pi. And then the inverse tangent, also known as arctan x, it takes in any real number whatsoever, and then it's going to spit out something strictly between -π/2 and +π/2. Now note that the domain of the inverse sine function is equal to the range of the sine function, and similarly for cosine x and tan x and their inverses. It's always the case that for a function f and its inverse function f inverse, the range of f equals the domain of f inverse, and the domain of f equals the range of f inverse. That is always going to be the case for a given function and its inverse function. But we want to get some practice ultimately here with finding values of these inverse trig functions. We want to know how can we find values of these guys. So we're going to do essentially the same process for all three cases, whether we're finding values of arc sine, arc cosine, or arc tan. In the notes, I have it written out for each case because there are some minor details that we have to pay attention to. If we want to find values of the inverse sine function, or arc sine x, take your quantity that you're given, set it equal to theta. You're then going to take the sine of both sides. And when you do that, you're just rewriting your given quantity as sine of this theta thing that we're trying to find is equal to your known value x. X will be given to you within the problem. And the thing to keep in mind when trying to find theta is that theta has to be between or equal to -π/2 and +π/2. And then you have to find the value of theta that satisfies that given equality that you have. You have to find that theta value from our previous knowledge of finding values of the trig functions at certain angles. And it's a similar kind of thing for finding values of the inverse cosine. The only difference is for the inverse cosine, your theta values there are going to be between 0 and pi. And then for the inverse tangent function, your theta values are going to be strictly between -π/2 and +π/2. So let's go through some sample problems. Let's see how we solve these guys. So we're going to find the value of each of these things here. Let's find the inverse tangent of minus the square root of 3. So first step, I'm going to take this thing that I'm given, I'm going to set it equal to theta. Really easy, just first step is always that. Second step, I'm going to take the tangent of both sides. Or really what I'm doing is I'm just rewriting this as the tangent of theta equals minus the square root of 3. Here's the most difficult part of this whole thing. Here's the trickiest part. Coming up with the angle that we have to plug into the tangent function to come up with minus the square root of 3. Okay, well, referring earlier on in the chapter, we had our table of nice, quote unquote, values of our trig functions. And we know that when theta is equal to 60, that the tangent of theta is equal to the positive square root of 3. So that's almost what we want, but we want minus the square root of 3. Now, earlier on in the chapter, we also learned that the tangent function is odd. So I know that if I take theta as minus 60, then the tangent of minus 60 equals minus the tangent of 60. That's my odd property there, and that's equal to minus the square root of 3. And that's what I'm looking for. I'm looking for that theta value right there of minus 60. However, when we write the values of the outputs for the inverse trig functions, we write them in radian form. So what we actually want is to write minus 60 in radian form, or theta equals minus pi divided by 3. So that is the answer that we want in the end. Again, for the inverse tangent function, our theta value has to be between minus pi over 2 and positive pi over 2, and minus pi over 3 is exactly that. All right, next one up, the inverse cosine of the square root of 3 over 2. Again, I'm going to start off the same way. I'm just going to take this thing here and set it equal to theta. So theta equals the inverse cosine of radical 3 over 2. I'm going to take the cosine of both sides, or I'm just going to rewrite it as cosine of theta equals radical 3 over 2. Now I need to think of the angle such that when I plug it into the cosine function, I get the square root of 3 over 2 out. And this one is significantly nicer. If you refer back to your table from earlier on in this chapter, you will recall that the angle that makes this true is equal to 30 degrees. But again, we write this in radians form, so it's pi over 6. Again, recall that when you're writing values of the inverse cosine function, your angle theta has to be between 0 and pi. And that's exactly what we have here, so we're good. I'm going to challenge you guys. Try this third one on your own here. Try to figure out what is the inverse sine of minus the square root of 2 over 2. Again, start off by setting this thing equal to theta, then rewrite it as sine of theta equals minus radical 2 over 2, and then the key piece, but also the most challenging piece, is finding that angle theta that will give you this value out. So press pause. Once you think you have the answer, press play, and we'll see if you were correct. Okay, so let's see if you came up with the correct answer. As we said, sine of theta equals minus the square root of 2 over 2. So what angle do I have to plug into the sine function to give me minus radical 2 over 2 out? Well, I know that if theta is equal to 45, then sine of theta equals positive radical 2 over 2. But that's almost what we want, but not quite. I also know that the sine function is odd. So if I plug in the negative of this angle into my sine function, then I'm going to get out the negative of this value. And the negative of this value is what I want. So that means I need theta is equal to minus 45, or in radians, minus pi over 4. So that right there is my final answer, and just our final answers from the previous two problems. So these were just a few practice problems of this type. This is really testing you on, do you know the values of your trig functions at these nice angles? And again, I put nice in some air quotes there because are they really the nicest? No. But this is really going to make you master your knowledge of the values of your trig functions. If you thought this was as hard as it's going to be, not quite. Let's kick it up another notch. We're going to get a little bit more complicated here. So we're going to find, to kick off, the cosine of the inverse sine of positive 1 here. You might be thinking, okay, what the heck am I supposed to do? If you see a problem like this, where you're finding the cosine of the inverse whatever of something, or just a trig function evaluated at the inverse trig function evaluated at something, isolate the inside and deal with the inside first. And to deal with the inside, you're going to do exactly what we just did in our three previous problems. Once you've found the inside, you're going to take that value that you get, and then you're going to plug it into your outside trig function there. So for now, I'm just dealing with what is the inverse sine of positive 1. So I'm going to set that thing equal to theta. I'm going to rewrite it by taking the sine of both sides. I need the angle theta such that when I plug it into the sine function, I get a positive 1 out. And if you refer back to your chart, or if you just know from your studies or whatever, if I take sine of 90 or sine of pi over 2, that's going to give me 1. So theta, in this case, is equal to pi over 2. So this thing right here, now to solve my problem, is what's going to be plugged in right there. So this is actually equal to the cosine of pi over 2, or the cosine of 90, and you can verify in your calculator that the cosine of pi over 2 or the cosine of 90 is 0. So we're just adding one more step onto the end of what we did in the three previous practice problems, just one little extra calculation. Here, the sine of the inverse tangent of 1. Again, I'm going to deal with that inside first, find what that is, then take that value and substitute it into the sine function. Theta is going to equal the inverse tangent of 1. That implies that tan of theta is going to equal positive 1. What angle do we plug into the tangent function to get a positive 1 out? If you refer back to our chart, or you just know off the top of your head, you find that theta is equal to pi over 4. So this angle getting plugged in now, and this thing is now going to equal the sine of pi over 4, and the sine of pi over 4, or the sine of 45, is equal to radical 2 over 2. So there is our second problem there. Try this last one on your own. Try to find the tangent of the inverse cosine of minus radical 2 over 2. So once you think you have the answer, press play on your video and see if you came up with the correct answer. All right, so let's see if you came up with the correct answer here. Again, I'm just working with that inside. I'm just going to set that thing equal to theta. I'm going to rewrite this as cosine of theta equals minus radical 2 over 2. And I'm going to solve for theta. The angle that I need to plug into the cosine function to get minus radical 2 over 2, this one was a little bit more tricky. This one is theta equals 3 pi over 4. Positive pi over 4 would get me positive radical 2 over 2, but to get minus radical 2 over 2, I would need 3 pi over 4. So this angle gets plugged in there, and this is going to equal the tangent of 3 pi over 4. And 3 pi over 4 in terms of degrees is 135. That lies in quadrant 2. The reference angle for 135 then, going a little bit farther back, is equal to 45. So the tangent of 135 and the tangent of 45 are the same magnitude. Are they the same sign though? Well, in quadrant 2, the tangent function is negative. In quadrant 1, the tangent function is positive. So I do need to multiply by that minus 1 there. So I get minus the tangent of 45, which is equal to a negative 1. So yes, that last problem was a little bit more involved, a little bit more complicated, but still something that you should be able to handle. The big thing in this section is obviously finding the value of the inverse trig function. The way that we do that, again, we saw in these 3 problems as well as the previous few problems that we did. And lastly, I just want to show you how these functions interact with each other. The functions and their inverses. Big thing to keep in mind is what is the inside function and what what value are you plugging into which thing here. It can be very easy to figure out what that is, or it can be a little bit tricky based on what value you're trying to plug into. If your inverse trig function is on the inside, like for this first one here or here, as long as you're plugging in something between or equal to -1 and +1, then you can use this guy here. Or for any real number x, the tangent of the inverse tangent of x, you can do that. But let me show you why you have to be careful as to what you're plugging in. If I ask what is the sine of the inverse sine of 1/2. Well, this 1/2 here is being plugged into the inverse sine function here. The ultimate question is this value in the domain of this function here? If it is, then we can use this property here and just say that the answer is just my x value, or in this case 1/2. If it's not in the domain, then this thing does not make sense, and we can't give any answer whatsoever. We would say that it is not defined. Well, 1/2 is between -1 and +1, so yes, this thing does make sense. 1/2 is in the domain of the inverse sine function, so we can say that yes, this is equal to just 1/2. Here's an example of something that would not make sense. If I had the inverse cosine of the cosine of 3 pi over 2. Because we're looking at the trig function cosine in the context of its in the context so that we can have the inverse function, the arc cosine or the inverse cosine, we can only plug in x values between or equal to 0 and pi. But here we have the value 3 pi over 2 being plugged into cosine x. And 3 pi over 2 is greater than pi. So this thing is not defined. Technically, could you do these calculations separately and come up with something? Yes. Technically, you could do the cosine of 3 pi over 2 and you would get a number, and then you could take that number, plug it into the inverse cosine, and get something out. But as a composition here, because this input here is not in the domain of my inside function here, because again, it's cosine, we have to use values between or equal to 0 and pi. Because it doesn't fall within there, we have to say that this thing is not defined. You're going to see questions like this on your homework, and that's the one thing you have to be very, very careful with. Does the value that you're plugging in truly fall within the domain of your inside function here? And the inside function, if it's just the trig function itself, just sine, just cosine, or just tangent, you have to be sure to restrict it to the intervals that we use on which we can have our inverse trig functions. So guys, that concludes this video on inverse trig functions. How do we get them? What these things look like? How do we find values of these inverse trig functions? In the next video, we're just going to touch on a couple more things, and then we are going to begin a new chapter, and we're going to kick it off with verifying trig identities. So if you have any questions or comments, please be sure to reach out to me, send me emails, snail mails, whatever you have to do. Otherwise, until the next video, take it easy.